This video is on the Taylor and Maclaurin series. For this one, I'm just going to do one problem on the Maclaurin series. Here's a formula for a power series. If you have a function and you're going to do a summation, you're eventually going to do a summation from n equals 0 to infinity. We're going to plug this in. And if we start off, if you notice, this right here is, this symbol here is what derivative are you taking? So first, since n is 0, we're not taking the derivative. If this function has a 0 up here, it's saying we're not taking the derivative. That's the starting out function. And then when n is 1, we're taking the first derivative. N is 2, we're taking the second derivative. N is 3, we're taking the third derivative. So I just wanted you to see what that n meant. It means the derivative of the function. And then it's times, you're plugging c into the function itself once you take the derivative, and you're dividing it by n factorial. All right, so that's pretty much a standard power series, which is really similar to the Maclaurin and Taylor series. Once again, here is the Maclaurin and Taylor series, what we just saw for a power series, with this little x plus c to a power of n. So there's the entire summation, and we're going to do each one. I'm going to be able to write each of the steps as we go from n0 to infinity, and we'll do 3 or 4 of them, and that's about it. So now, this is called the Taylor series. However, do you see the notation? If c equals 0 in the notation, then it's called the Maclaurin series. So the Taylor series, c is something other than 0. But if c is 0, then it's called the Maclaurin series. And that's what I want to look at first, a Maclaurin series problem. So here is our function. It says to form a Maclaurin series. In other words, we know if we say Maclaurin, then c equals 0 in our function. So I'm going to come back and write this down, fnc n factorial x minus c to a power of n, if I can remember all that. This is the function f, the n, c divided by n factorial. And then we're going to multiply it by x minus c n to the power. So when we go back, this is our function. This is what we're using. And it's a summation. This is how we do the summation. And the summation's from 0 to infinity. So to do this, the first thing you want to do is find all the functions that you're going to use for each section. Do you see this function n? This n stands for the derivative. So first, we're not taking the derivative of the function. Then we're going to take the first derivative, the second derivative, the third derivative, and the fourth derivative. So here, let's start writing these functions down. Here's our function x, the function f. Without the derivative, our answer is the sine of x. That's our function. Now, if we take the first derivative of sine of x, we get cosine of x. If we take the second derivative of cosine x, we get negative sine x. If we take the third derivative of negative sine x, we get negative cosine x. And you can keep on, that's the third derivative, sorry. And if you keep on going, if you take the fourth derivative, that's the third, maybe I should just write a 3. If we take the fourth derivative and we change it back to sine x, we bring the negative out. Negative is a positive. And so on and so on. So you can keep on taking the derivative of that. So here's the function. I want to show you what we're getting here now. We're going to rewrite this function first with this function here. N is 0. Do you see? This is the 0 function. There's no derivative. And we're going to plug 0 into it. Go back up. I keep on showing you that. Go back up. This is C. And we said for Maclaurin series, C equals 0. So we're always plugging 0 into the function. I should have left some room here. What happens to all of these when I plug 0 into x? Let's find out what happens to all of these when I plug 0 into it. If you look at the sign of 0 is 0. The cosine of 0 is 1. Sine of 0 is 0. Cosine of 0 is 1, but there's a negative in front. The sine of 0 is 0. You see, we can keep on going with that. So we know when we plug 0 into each of these functions, we're going to get 1, 0, 1, 0, 0, negative 1. We're plugging 0 into each of these functions. Okay, so this first one, they don't show you, but I'm going to show you the whole step for this first one. First, we plug in 0 into the function, and that's without the derivative. Then we do x minus c. And our very first step, n is 0. So we're putting a 0 up here. And it's divided by n factorial, which is 0 factorial. Well, by the way, c is 0 in our case. We can put a 0 here. X minus 0 to the 0 power is going to be 1. This changes x to the 0 power, anything to the 0 power changes to 1, sorry. 0 factorial is 1. So when we simplify all this, we're just dealing with f to the 0 power, just like we have up here. So next, we're going to do the same thing, but we're using the derivative. So we're going to use the first derivative of f and put 0 in it. X minus 0, which is just x, to the 1 power divided by 1 factorial, because we're using n1 now. X to the 1 power is x. 1 factorial is still 1. So this becomes the first derivative, plugging 0 in. X to the 1 power is x, and 1 factorial is 1 divided by 1. And that's how we get this. I'm going to do the second derivative now. Second derivative, we're plugging 0 in. And if you notice, if we put a 2 here, we have x to the second power. And then we have 2 factorial. And 2 factorial is just 2. So we're going to go second power is 0, x squared, and then I'll leave it as 2 factorial. The next one will be f to the third power, plugging 0 in, x to the third, and then 3 factorial, and so on and so on. You see, that's how these get formed, by using this, starting with n0 going to n1. So this is where we're at now. So the only thing we need to do is plug 0 into the first function, plug 0 into the first derivative, plug 0 into the second derivative, and we have our series. So if you know, let me change color here. If I plug 0 into the first function, here's the first function. If I plug 0 into it, I get 0. If I plug 0 into the second function, I get 1. So this ends up being 1 times x. If I plug 0 into the second function, I get 0. This becomes 0. 0 times anything is going to be 0. If I put 0 into the third function, I end up with a negative 1. And we're talking about then x to the 3. And 3 factorial is 6. This should be a 6 on the bottom. There we go. And so on, and so on. So our I should do one more. If we ended up with I should have did one more, but I think the next one 4 would be 0. If you look, if the next one 4 would have been 0, because we had a 0 here, and then we have a 5. 5 would have been a positive. The f5 would have been cosine x, which would have been a positive 1. So the 4 would be 0, but then the 5 would be a positive 1. The function would be 1 times x to the 5 over 5 factorial. So if we look at this whole thing, we have 0 as the first term. Then we have x as the second term. Then we have 0 as the third term. And we have negative x to the third over 6. Oh, x to the third over 3 factorial, which is 6. And that's a negative. I'm just going to leave it there now. And then we have 0 as the next term. The fourth term was 0. And the last term is x to the 5 divided by 5 factorial. And 5 factorial is 5 times 4, which is 20, times 3, which is 60, times 2 is 120. So if you look at this, this is x minus x to the third over 6 plus x to the fifth over 120. And we can actually, I think they keep it, when they actually do this, they don't multiply this out. This is the 3 factorial, and this was the 5 factorial. They don't actually multiply that out. So these are the what the summation would look like: 0 plus x plus 0 plus negative x to the third over 6 plus 0 plus x to the fifth over 120. So this is what it would look like. Can we write this? Can we write this in one simple term if we look at that. Don't forget, we're doing a summation. We're doing a summation from n equals 2 to from n equals 0 to infinity. So can we write this as a summation? If you notice, it goes positive, negative, positive. The next one would be negative. It would be x7. The next one would be, if you keep on going, positive, it would be x9. So it's going negative, positive, negative, positive. The only way to get one term as a negative and a positive, the top, we'd have to multiply the top by -1. And since we're starting, if we're starting at 0, the only way to get from negative, positive, if we start at 0 there, we're going to put that -1, raise it to the n power, and I'll show you what we do. Do you see this is n of 1? N equals 1. This is n equals 2, which is still positive. There, once again, this is n equals 2. If you put 2 in there, -1 squared is a positive, so we have a positive. And this is n equals 3, and 3 we should have a negative. If you put a 3 into this n, -1 to the third power is a negative. So this is how you would switch from -1 to +1, negative to positive, using a -1 to a power sign. Now we have to figure out how to switch 0, go from 0 to x, then back to 0 to 3. So when we're looking at the symbol, this final product that we have up here, I'm not looking at this top one. I'm looking at the second row. We go 1, 3, 5, 1, 3, 5, 7. So I need to write a way of doing that. So it's going to be an x, and we want it to start off with a power of 1. But this starts with n is 0. So the only way to start off with a power of 1 when n is 0 is by putting a n plus 1 here. Do you see now if I have put a 0 in there, I have an x of 1. However, it actually, this x should be a 2 in there. I'm trying to look at this paper. So we're looking at this series. If we start at a 0, we should have a 1 in, when we start at 0, we should have a 1 in here. It is really hard to explain. And since we're going by odd numbers, we're skipping 2s, you have to multiply this by 1. Let's see if this makes any sense. Let me put this into parentheses. So 2n plus 1. Do you see in this problem, if n equals 0, that's where our summation starts. If n equals 0, then my power is 1. If n equals 1, then my power is 3. If n equals 2, then my power is 5. 2 times 2 plus 1 is 5. You see, that's what we're doing. Our power is 1, 3, 5. So we're using 2n plus 1 when n, and I keep on, this is really hard to see, but this is n0. So we're using 2n plus 1 to signify that we're going from 1, 3, 5, then 7, and so on and so on. So the only thing we need to do now is the bottom, and we're doing the same thing on the bottom. Do you see the bottom is this bottom matches the bottom. There's a 1 factorial down here, which is 1. And down here, this is 3 factorial. It matches this power. The bottom matches this power, 5 factorial. So to get the way we got the powers up here is the same way we're going to get the numbers down there. And we're going to use 2 plus 1 factorial. So this is the actual formula to do this Maclaurin series. This is the actual formula for the summation. Now I can plug 0 in there and get the first term, plug 1 in there, get the second term, plug 0 into the formula, I get this first term. Plug 1 into the formula, I get the second term. Plug 2 into the formula, I get the third term. So this is the summation of the Maclaurin series. And these are the terms of the Maclaurin series. These are the terms. And this is what the function actually looks like. The final summation function looks like to do the actual summation. I know that was a little confusing on the explanation. There's a little work. The only work really is that taking the derivative of each of those functions, and then you're just plugging it into the formula. The hard part, I think is not doing these terms, but the hard part is seeing how all those terms form into a formula that we're going to, a final formula that we use for the Maclaurin series. Changing the power series to an actual Maclaurin formula that we could now justify each term. You see, these are not the terms of the Maclaurin series because they're zeros. So we're using these, and this formula gets us to that. First, we had to get to this to get to this, and then we needed to create this formula from the pattern that we noticed. All right, well, I hope that Maclaurin series helps out. I do want to show you, this is, they just show the power series that we just did here. They just went through the problem and said by the ratio test, you conclude this series converges. But I did want to show this from the book. It shows the elementary functions and what their power series looks like. If you had the function 1/2. Once again, just doing a power series on each of these functions, going back and looking at that power series formula, you can see what each of these functions would look like. And we just did the sinx, and there's the sinx that we just created. And the Maclaurin series is when C equals 0. Don't forget about that. That Maclaurin series is when C equals 0. All right. If you have any questions, feel free to contact me.